Welcome, everyone. Thank you for joining us today for the Molecular Connectivity online series, or MCOS. My name is Xindi from New Jersey Institute of Technology. In case you are new here, the Molecular Connectivity Working Group is a group of scientists that aim to advance molecular imaging as a tool to study brain connectivity. We organize this online series as a platform to promote ideas and research on molecular connectivity. You can go to our website, subscribe to our newsletters, and follow us on Twitter and LinkedIn. So today, I'm happy to introduce our speaker, Dr. Silvia Caminiti. She is an assistant professor at the Department of Brain and Behavior Sciences at the University of Pavia in Italy. With a background in neuroimaging and neuroscience, Dr. Caminiti's primary research focus evolves around aging and neurodegenerative disorders. The goal of her research program is to examine selective neuronal vulnerability in Alzheimer's disease and Parkinson's disease using multimodal neuroimaging, including PET and MRI. In today's talk, she will talk about the dark side of hyperconnectivity, a metabolic prelude to neurodegenerations in Alzheimer's diseases. Once again, welcome, and let's welcome Dr. Caminiti.
Thank you very much, Sin, for this presentation. Let's start by sharing my slides. Okay, perfect. Removing this one. And okay, can you see the pointer?
Yes. Good.
Yeah, perfect. Okay, good afternoon, everybody. Yes, this presentation deals with research study that was already published in the European Journal Nuclear Medicine Molecular Imaging Journal. In this study, we wanted to explore the dynamic change in connectivity, metabolic connectivity in Alzheimer's disease continuum. And in particular, we want to explore the role of hyperconnectivity in this continuum. Before speaking about the results of my study, let's start introducing what is hyperconnectivity and why we consider it a crucial aspect for Alzheimer's disease. Indeed, a common finding is that damage to neural system may paradoxically result in hyperconnectivity. But what is hyperconnectivity? Hyperconnectivity derives from a comparison between two groups of patients two groups of subjects, one group of patients or one patient and one healthy controls, for example. So is a connection that change as respect to healthy controls to the reference group in terms of number and strength of neural connection, but may also be observed in the same group of subjects before and after one event, for example, a brain injury. A well-functioning network is defined as scale-free network because a complex network is characterized by modularity, that is the organization into distinct but interconnected functional modules or sub-networks, and by the presence of very limited number of nodes with a high connectivity degree, so that are the hubs of the network as respect to the other nodes. These hubs may have evolved as a consequence of a preferential attachment dynamics. During network development, some nodes with a high degree of connectivity continue to gain more connection and are defined as the rich that can get richer. And a scale-free network exhibit what is the role of the scale-free network. This network may exhibit remarkable resistance to random damage. As you can see from these two graphs, one for nodal resilience and the other for edge, the networks with a very good functionality present hub with the resilience to random attack, so attack to other nodes of the network that are isolated. But if in this simulation, the attack is targeted to the nodes, the most important nodes, that's the hubs of the network. It results in a loss of global efficiency, as you can see in the red line. So this suggests that okay, these apps are important for for maintaining the brain structural integrity and communication capacity, but are at the same time very vulnerable to disease attacks. One of the proposed models that try to explain hyperconnectivity in neurodegenerative condition is a nonlinear model in which after mild damage, they postulate that there is a mild primary response characterized by initial loss of connectivity, but immediately associated with a secondary response of hyperconnectivity that is made by a network that is able to compensate this mild damage. So this results with mild or non-behavioral deficits, so no clinical evidence of alteration. Sorry, when don't know why, what's up here? Should come the other. Don't know why it can't. Okay, there should be another line here. I don't know why it doesn't disappear. Anyway, another aspect of severe damage is a very sustained hypoconnectivity, a red line here, that is without a hyperconnectivity response. So according to this model, that is not the last model, the hyperconnectivity is just an early event that is a compensatory response that allowed the brain to respond in a resilient way to brain initial small mild injury. However, with the advent of multimodal neuroimaging approaches, we had the opportunity to explore the link between connectivity and effective underlying pathology. In this seminal study of Buchner et al., we can see that the Fulmon network, the network that is the most important and most connected network in the healthy brain that was derived in two independent data sets, presented some hubs, important hubs. And these hubs, in particular in associative cortex and precuneus, parietal and posterior cingulate cortex, are regions that resulted in Alzheimer's disease very highly vulnerable, affected by amyloid pathology, uptake from PET, but also accumulation of this pathology by postmortem evidence. So here you can see that they reported a linear relationship, strong relationship between the nodes connectivity, degree of connectivity, and in the same nodes, the A-beta deposition. So this further supported the idea that these nodes that are very important for the network functionality are at the same time very vulnerable to pathology for Alzheimer's disease. And this was supported by other cell and animal models in which there was reported that A-beta trigger neural hyperexcitability, increased neural firing, and hypersynchronicity in cells and animal models in terms of increased glutamate release, reduced GABA sensitivity, and augmented influx of calcium. So in this context of presence of this hyperconnectivity, chronic hyperconnectivity, we can't believe that this hyperconnectivity is just an early response, compensatory mechanism that is isolated in the early phase of Alzheimer's disease continuum. So, according to this other model, the ADD model, activity-dependent degeneration model, in early stage, highly connected default network hubs show elevated activity, leading to activity-related amyloid pathology accumulation. During the MCI phase, A-beta-driven hyperactivity increases network stress and promotes the tau propagation that is accompanied by an initial structural connectivity reduction, but increase of functional connectivity and increase of amyloid pathology, linear increase. As in the final part in Alzheimer's disease stage, when the tau mediated degeneration has affected both structural and functional connectivity, this phase is characterized by a very deep and important degeneration and also disconnection of the default mode network. This relationship between amyloid beta and tau pathology and the spreading of these two, the latter, the tau pathology through the network, the connectivity network, has been recently supported by evidence again in Alzheimer's disease, in which they studied both tau epicenter of pathology, so where the tau tends to accumulate more in Alzheimer's disease, and they found that this accumulation in the medial temporal lobe of tau can induce this hyperconnectivity, particularly between the temporal lobe and the default mode network regions. And this hyperconnectivity is associated with an accelerated spreading of tau pathology across the network. Another evidence that is related to the important role of the medial temporal lobe, in particular in terms of hyperconnectivity, is related to this study in which they investigate medial temporal lobe connection to the posterior medial default mode network regions and the other connection to the anterior temporal cortex, anterior temporal lobe. They found that in Alzheimer's disease, just in Alzheimer's disease, these two networks tend to have an opposite behavior. So, of course, the medial temporal lobe to the default mode network show a disconnection. Instead, the medial temporal lobe to the anterior temporal part showed an hyperconnectivity in Alzheimer's disease. And these two networks, both associated, showed a prediction of cognitive decline in this group of patients, in MCI, sorry. So suggesting that there is a interlinked role of these two activity and is not just an early response to neurodegeneration. I would like to talk also about this study that we published really recently, but not about connectivity. In this study, we want to explore brain metabolism in amnestic MCI subject from two independent cohorts, ADNI and another consortium, in which we explored the pattern of brain hypometabolism, and we stratify into three different groups, main subgroups. One group characterized by prevalent cortical hypometabolism without involvement of the medial temporal lobe. Another one with both hypometabolism in temporoparietal cortex as well as the cortical prevalence, but also hypometabolism of the medial temporal lobe. And another one characterized by just hypometabolism in the medial temporal lobe. Notably, we found that the group characterized by a severe hypometabolism, cortical metabolism, showed also a middle temporal lobe hypermetabolism that was not present in any of the other subgroups. And this group, the cortical subgroup and the middle temporal lobe hypometabolism were in an opposite position for the clinical aspect. Indeed, this cortical hypometabolism with middle temporal lobe hypermetabolism was characterized by a very high level of conversion to dementia due to AD follow-up. In the opposite way, the middle temporal prevalence was characterized by very low risk of dementia conversion and a clinical stable clinical phenotype over time. So again, this hyperactivity of the middle temporal lobe suggests something that is may support an early sign of a more severe trajectory in Alzheimer's disease. So in this study, we wanted to combine both the information of connectivity with the underlying hypometabolism in our cohort of patients, and also information about clinical evolution. Indeed, we wanted to assess connectivity rearrangement in the AD continuums in terms of both hypo and hyperconnectivity. Then we want to identify both stage-specific and longitudinal connectivity patterns by means of a clustering approach. And then we want to assess how the longitudinal connectivity patterns, so the pattern of connectivity that are consistently available, consistently reliable in the AD continuum, are related to glucose metabolism and may predict risk of conversion to dementia. To do so, we included a cohort from ADNI, and we had the great opportunity to study the same group of patients with amnestic MCI, 31 patients with all available clinical information and also structural MR and FDG-PET. Then we followed them till the moment in which the neurologist changed the diagnosis from MCI to dementia. And we acquired the same information co-registered to this moment, and then we acquired information of the last stage, more than 2 years follow-up, in which the diagnosis of dementia was really established and stably assessed. To obtain information about hypo and hyperconnectivity, we wanted to compare this group of patients with a group of healthy controls. To do so, we included an age-sex matched healthy control subject with the same information available, but clinical stability and that's had available also at the same time point this information. So we were able to co-register these patients to each time point. The other important aspect was that all patients were amyloid positive, tau positive, and neurodegenerative positive in terms of pattern of AD-like pattern of brain hypometabolism. We ran this single subject procedure and we evaluated it. Every subject presented this temporoparietal and precuneus and posterior cingulate cortex hypometabolism. At the same time, all healthy controls were ATN negative. Okay, what about the procedure? We constructed our network. We included FDG-PET, T1 structural MRI, and an atlas of regions. We obtained SUVR from FDG-PET, and we moved the FDG-PET to the native structural space. This allowed us to, the same time, move the atlas to the native space, perform a masking with the gray matter single subject mask obtained from each subject. So we obtained a single subject network from each patient, and also for healthy controls. Then we extracted from the atlas the SUVR, and we obtained our matrices, for one for MCI and the other for healthy control for each time. Then we ran Pearson correlation analysis, and we obtained adjacent matrix for MCI and healthy controls at each time point. We compared these two matrices, obtaining by means of Z-test, and we obtained this Z-score, indicating positive Z-score indicates greater connectivity as respect to controls, so hyperconnectivity in patients, and lower negative Z-score, indicated hypoconnectivity compared to controls. Then we performed two different k-means analysis, clustering analysis. One, the KLM1 stage specific, in which we wanted just to explore the level of altered connection, so the nodes characterized by high level of altered connection for each time point. So we ran three different independent clustering analysis, and we inserted in this clustering analysis the mean Z score in absolute value. We didn't explore the sign or the level of hypo and hyperconnectivity. We want to explore this aspect in the longitudinal KLM2, in which we used four different indices of connectivity, the mean absolute Z again, but also the mean positive Z, so the average of just Z, positive Z score indicating hyperconnectivity, mean negative hypoconnectivity, and mean all Z that represented not in absolute value the average of all Z score. Then we concatenated all time point, T0, T1, T2, and we ran in a single run the KLM. In addition, we wanted to explore how these clusters of longitudinal cluster change in terms of metabolic values, SUVR values. So we perform a repeated measure ANOVA, in which we compare these SUVR values extracted from the longitudinal cluster across the three time points for both patients and controls. Then we perform a mediation analysis to test whether the relationship between mean metabolism in AD-like pattern, so in temporoparietal pattern, the change from T0 to T2 was mediated by any or some of the longitudinal cluster that emerged from our analysis. Then we perform also a linear regression model to assess the association between longitudinal clusters and time to clinical conversion to dementia. As you can see from the univariate analysis that just compare patients with healthy controls, the AD-like pattern, of course, was expressed at the beginning in the MCI phase, but across time didn't change anymore, just little bits of significant score, T-score, indicating that the univariate analysis to study the longitudinal progression of any pathology may not be so useful. In the other way, the connectivity, metabolic connectivity analysis show a dynamic change with some major similar results, in particular in the connection between parietal and occipital cortex to the frontal lobe, but there were differences in the different time points, at the different time points. And this was particularly relieved by our KLM1 that showed that the initial phase were characterized by prominent alteration, as you can see here, in connectivity linking posterior associative cortices to frontal regions. Over time, network disruption became more localized, in particular in the last phase, to the posterior part of the brain. So this was our first evidence. The KLM2 analysis, investigating the longitudinal aspect and the level of hypo and hyperconnectivity, identified three different clusters. Cluster 0 was consistently represented by low intensity connectivity change at 3 time points. And included middle cingulate cortex, temporal pole, and cerebellar cortex. Cluster 1, the green one, showed the highest hypoconnectivity in the precuneus, superior inferior parietal lobule, middle temporal lobule, occipital cortex, and ventromedial frontal cortex. The cluster 2 was the cluster encompassing region with greatest hyperconnectivity, namely regions of the regions where the hippocampus, amygdala, and vermis. Then we wanted to provide a label to this cluster, and we ran the network correspondence toolbox, and we found that cluster 0 showed no overlap with any canonical network, cluster 1 was identified as the default mode network, and cluster 2 with the limbic network, of course. Then we explored with our repeated ANOVA how this cluster were represented by underlying hypometabolism, metabolism level, and we found that all clusters showed lower metabolism compared to healthy controls, but among patients only cluster 1, the default mode network cluster, showed significant hypometabolism compared to the non-affected cluster 0. Instead, cluster 2 displayed a significant severe decrease over time between MCI phase and AD-MCI phase. And AD dementia phase. Again, cluster 2 was the only one that significantly mediated the change in brain hypometabolism from T0 to T2, so indicating that the level of metabolism in these regions considered high, hyperconnected, have a mediation effect on the level of change of hypometabolism in AD-like regions. And the same way, cluster 2 showed a positive association with the metabolism. Cluster 2 at T0 showed a prediction, significant prediction of clinical conversion to dementia follow-up. The time to clinical conversion, because everybody converted to dementia. So to summarize, the default mode network hypoconnectivity cluster showed the most severe hypometabolism and hypoconnectivity, but the same way hypometabolism since prodromal phase. The hyperconnected limbic cluster showed strongest longitudinal metabolic decrease, mediator of FDG-like parieto-temporal hypometabolism, and prediction of speed of conversion to dementia. So, what is the real role of the default mode network and the limbic network in this case of patients? So, in our case, default mode network, we showing the highest proportion of hypoconnectivity across time and also lower level of hypometabolism is consistent with the literature. Indeed, the default network, we well know that is in normal condition showed high resting metabolic activity and high baseline blood flow that reflect his high substantial energy consumption. This makes it very vulnerable to pathology from the beginning to the A-beta accumulation, and is also a transmodal network, so highly connected, integrated. This is a very good field for the tau pathology to propagate and to produce an early neural injury and neurodegeneration in the beginning of the disease. Instead, related to the limbic network, we, in the end, arise two different questions. So, could hyperconnectivity reflect early compensatory mechanism, where specific regions more connected to counterbalance the degenerational sphere, according to the crunch model? So, these regions are hyperconnected to, help the degeneration occurring in the default mode network, or does it reflect pathological mechanism in which amyloid beta pathology induce neural hyperactivity or network hyperconnectivity that we observe in this medial temporal lobe? So the results is not novel of hyperconnectivity in the medial temporal lobe in prodromal phase. Indeed, as you can see here in this study, this hyperconnectivity was observed also in preclinical phase, ApoE positive subject as compared to ApoE negative subject. This very nice model that take advantage of both tau accumulation in the epicenters of tau accumulation and also A-beta pathology and connectivity show that this accumulation tau and the deriving hyperconnectivity produce a very good framework for the propagation of A-beta and tau pathology affecting neurodegeneration. In addition, this A-beta and tau amplify network dysfunction via neuroinflammatory response, microglia activation, and synaptic collapse and neurodegeneration. So, of course, our results indicate that we can't say that by means of this clustering, longitudinal clustering approach, that hyperconnectivity is not an early event. It's an event that is, in particular in these regions, follow the whole disease course that we considered from MCI to dementia. And the metabolism in these specific regions is a good predictor of disease course and greater neurodegeneration in the default mode network and associative cortex areas. So this is just to conclude and thank Alice Galli, the first author of this work, and also our friends from the Molecular Connectivity Working Group, Daniela, Arianna, Exin, that have the pleasure to collaborate with for this project. Thank you very much, and feel free to do any question.
Thank you very much for the wonderful talk. So I think if anyone has a question, I think you can unmute and ask directly. I think right now there's one question in chat. So she said, I want to ask you a few questions related to k-means clustering. Could you please tell what is the input that given to the k-means clustering algorithm? Is that the Pearson correlation matrix?
No, we directly use the Z-score that we obtained from the comparison, the Z-test comparison between healthy controls and patients. And in this way, we use for each nodes, we perform an average of Z-score, absolute score, or dividing in the longitudinal analysis also according to the sign of the score, so into hypo and hyperconnectivity. So in the end, we have average values for each node indicating these different aspects.
Oh, maybe I just ask a few questions. I think it's really interesting. And you mentioned about like amyloid and so on. So I think in ADNI they also have that PET the PET scan, right? Have you tried to integrate that part in your analysis? And also, actually, they are also functional MRI or DTI or something because you are mentioning the differences between structure and functional connectivity. Maybe they are have different effects.
Yeah, maybe the next step. We was the first exploratory at the moment for molecular metabolic connectivity. And first of all, we would like to understand what is the what's the hyperconnectivity means in terms of hypometabolism because of our previous results on hypermetabolism in medial
Yeah.
temporal lobe.
And I think in fMRI literature in not pathology but like in healthy aging, they are trying to differentiate whether they are, for example, you have given a task and some of them individuals can do the task properly and some cannot, and then you compare them and you see some differences. Then that is a kind of a compensation. If they can perform the task, then maybe their hyperconnectivity can be interpreted as a compensation or something. So
Yeah.
of course that is before the pathology, but do you think that this task context, I assume that those in ADNI are all resting state, right? They are not doing
Mm.
that task. So how do you think that maybe the task context may affect this connectivity and the results?
This is a very interesting point because the main, I think that the main hypothesis about the role of hyperconnectivity and also hyperactivity of medial temporal lobe derives from these task studies. Indeed, for example, the one from APOE subject, preclinical subject showing hyperconnectivity. Also, they showed in a task-related paradigm that the hyperconnectivity predates their not they lower ability during task of memory and suggesting a vulnerability and something associated with pathology and predating the conversion to MCI maybe.
Yeah. And another question is, so I saw that you have these three clusters and then you gave it to the network toolbox. And I was a little surprised that you have one that you say you do not have a corresponding networks. So does that means that, so that networks given to you, is that the 7 networks from EO, or does that mean that the networks we identified using PET are actually very different from what we usually do find in fMRI? Do you have any sense of that?
Not so different for the default mode network. Because
Right.
the network showing the strongest hypoconnectivity seen from MCI to dementia is the network that is the full mode network. So we confirmed the results. The other network, the cluster 0,
Right.
is a network that is not affected,
Uh-huh.
but maybe random regions, maybe not related to connectivity, but regions that maybe should be more investigated because this cluster is very peculiar because it's consistently not affected in terms of connectivity. And also in terms of metabolism in general, we
Yeah.
didn't show any association with any of our specific variables of interest. So yeah, should be explored better, but are regions that almost are not related to AD pathology.
Okay. Yeah, but still, I mean, in normal subject, you are still should find networks, right? Like in
Yeah.
But this one is what I'm just wondering whether it is because head can measure something different from fMRI.
Yeah.
Why?
But we the clustering was driven by AD.
Oh yeah.
Not okay. So we just selected those regions or no group of nodes showing a peculiar behavior in AD. So maybe that are regions that are part of other networks normally that are combined because nodes not vulnerable in AD in our AD court.
Yeah. I think Igor had asked a question in the chat. So where there are differences in the hippocampal volumes from T1 to T3?
We didn't explore it. Okay, in our previous the MCI study, I show you about hypometabolism of the three subtypes that was also performed in with ADNI court. In the cortical, the three subtypes, we didn't find any difference in the volume of hippocampus. But hypometabolism and hypermetabolism, so in the MCI phase, but should be explored also the structural part. We use a structural just for preprocessing and extraction, network construction.
So have any questions from the audience? If anyone have questions, please unmute and then Chris to have questions. Yeah, it seems that oh, so it do you mean the clusters number?
No, yeah, okay. Yeah, there was no, I didn't I didn't put any constraint. So it was defined automatically. So putting just the average Z score in the first KLM, they just provide two clusters. They are the affected and unaffected cluster. And that I recognize post-hoc by analyzing the value of Z and the significance. And the other analysis provide three different clusters without constraint, a priori constraints.
Hi, Chris is unmuted.
No, I'm good. I'm good. Sorry. I thought it was very clear, but I don't want to turn this into a methods discussion, but yeah.
Okay.
Nice picture.
Oh, thank you. Thank you. It looks way better than I look in real life, for the people who haven't seen me.
It's olive oil effect.
Coffee and olive oil, yeah. I recommend it.
So you basically the ADNI is a very good resources. Do you know that there are any other like resources we can use to study like Alzheimer's and MCI? I know there's also WashU, right? Also have one big data set, but I don't know whether they have longitudinal or right now only the ADNI, right?
The main issue was to find really this cohort of patients, because we wanted to explore, we controlled every aspect, I hope every, and we want to explore when the neurologists change the diagnosis and have the same for each subject. So we don't have time points that are define the different follow-up with time frame that was predefined, but we want to follow the natural course of the disease. And for this reason, then we had to match the healthy controls to our patients to have a reference related to age and sex and staging time. But really was in ADNI we have a lot of data, but in the end we collect just data from 31 subjects.
Yeah.
It was really quite difficult.
Right. Yeah, and they actually have like multiple runs, right? And you said you just choose 3 time points. And then do you feel that phenomenon they actually started maybe in 2000 something, and then they're already now think about like maybe 20 years. So all the techniques have changed, the quality of the images have already changed. So how do you think that may affect the results of the PET of the longitudinal studies in the ADNI dataset?
I don't know.
I remember when I first time I analyzed the PET, they all have this kind of like streak. It's like the reconstruction is done using a very
Okay.
Then
Yeah.
now then they have some. I think they have reconstructed better in a way that you do not see that kind of streak. So I think they have updated for that part. I'm not sure, but I feel the quality of the earlier data and the later data may not be comparable, and I'm not sure.
Yeah, we try to use the standardized image, but you are right. And for this reason, after I started to use, for example, neurocombat to try to harmonize this aspect, because it's emerging as an important aspect, in particular the machine, the change of machine, reconstruction, everything is affecting our results. So even if you are studying the same subject, but these are important aspects. With the neurocombat, you can try to harmonize this aspect, the reconstruction and also the different machine used.
Right. Okay. Have any other questions? So I just have provide a link to the feedback. If you want to give us feedback, please click the link. And also for the next month, we will have a seminar we have invited 4 speakers who have discussed about the validation of molecular connectivity. Welcome to join. So I have any others in the audience have questions? Please feel free to just unmute. We can have a discussion.
Okay. It's enough for Friday.
Yeah,
Friday
I know that. I see.
afternoon.
I asked a lot of people come, and I say, okay, well, I will have to leave early because it's a Friday afternoon. I see that in Europe. So okay. So if let's conclude here today, and thank you for all coming, and hopefully see you next month. Thank you. Thank you
Thank
for
you
everyone.
very much.
Yeah.
Bye.
Have a good weekend.
Bye.
Bye bye.